In this section, we are going to talk about fundamental theorem of arithmetic. We'll start with natural number and we'll see every natural number can be expressed as product of their prime factors. Then we'll talk about what is fundamental theorem of arithmetic. And then we'll talk about prime factorization method examples. So let's start with any natural number can be written as product of its prime factor. So remember what is prime number first, right? So a prime number is a whole number, right? It's a whole number greater than 1 whose only factors are 1 and itself. So any number can be a prime number if they are greater than 1 and they are whole number, and they can only be divided by 1 or itself. And what we are talking here is if I pick any natural number, I can always represent them as product of prime factors. Now let's take some examples. 2 itself is a prime number, and if you try to express 2 as product of prime factors, you get 2. However, if you take 4, which is not a prime number for sure because it can be divided by 2, which is different than 1 and itself, and hence we know we can express 4 as 2 multiplied by 2, but this 2 itself is a prime number, and hence 4 can be expressed as product of prime factors. Similarly, 253 can be expressed as 11 multiplied by 23, where 11 and 23 both are prime numbers, and hence 253 has been represented as prime factor of prime numbers. Now let's take an example of 32760. Can we represent that as product of prime factors? And the answer is yes. You can divide 32760 by 2 and what you get is 16380. You can further divide it by 2. What you get is 8190, which can further be divided by 2 and you get 4095, which then gets divided by 3 and gives you 1365. And then you can divide it by 3 again and you get 455, which can then be divided by 5 to give you 91, which can then be divided by 7 to give you 13. Now if you look, 2, 2, 2, 3, 3, 5, 7, 13, they are all prime numbers, and hence 32760 can be expressed as product of prime factors like 2, 3, 5, 7, 13 raised to some power. In this case 2q multiplied by 3 square multiplied by 5 multiplied by 7 multiplied by 13. Now let's try to understand what is fundamental theorem of arithmetic, what it says, right? So what it says is every composite number can be expressed or factorized as product of primes, and this factorization is unique apart from the order in which the prime factors occur, right? So basically every number can be expressed as product of prime numbers raised to some power, and these prime numbers are going to be unique. So continuation of fundamental theorem of arithmetic, right? The prime factorization of natural number is unique except for the order of its factors, right? So in general, given a composite number x, we factorize it as x can be represented as product of p1, p2 dot 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 up to pn, where p1 to pn are all primes, that is prime numbers, and are written in the ascending order, where p1 is less than, p2 is less than or equal to dot dot dot, which is less than equal to pn. If we combine the same primes, we get power of primes, And that's why any number can be represented as product of prime raised to some powers. For example, 32760, which we have seen in the previous slide, is expressed as 2 multiplied by 2 multiplied by 2 multiplied by 3 multiplied by 3 multiplied by 5 multiplied by 7 multiplied by 13, and now you can express that as unique, which is 2, 3, 5, 7, 13 raised to some power. So 2 raised to the power 3, 3 raised to the power 2, 5 raised to the power 1, 7 raised to the power 1, 13 raised to the power 1 gives you 32760. Now let's take some example of prime factorization method, right? Now in order to do that example, we'll try to find out LCM and HCF of two numbers 6 and 20 by using prime factorization method. We know we can represent 6 as 2 multiplied by 3, and you can see 2 and 3 are all prime numbers, and hence 6 can be represented as product of prime factors. Similarly, 20 can be represented as 2 multiplied by 2 multiplied by 5, which is nothing but 2 square multiplied by 5, and in this case 2 and 5 are prime. And hence HCF of 6 and 20 is 2, and LCM of 6 and 20 is 2 into 2 into 3 into 5 is equal to 60. How is this calculated? Let's take a look. Remember, HCF of 6 and 20 is equal to 2 to the power 1, which is nothing but product of the smallest power of each common prime factors in the numbers. What it means, I had numbers 6 and 20, I break them into prime factors, and now I'm going to look what is common between these two when I look the prime numbers, and I can see between these two prime factors the number which is common is 2, and now I have to look what is the minimum power for that prime number, and the minimum power between 2 to the power 1 and 2 to the power 2 is 1, and hence my HCF of 6 and 20 is 2 to the power 1. So two things, I will look what is common primes between the two numbers, and then I will look what is the least power I have on the common primes. That gives me HCF. Similarly, LCM between those two numbers are 2 square multiplied by 3 to the power 1 multiplied by 5 to the power 1, which in turn is basically product of greatest power of each prime factors involved in the numbers. So what it means, you look both the prime numbers, look for all the distinct prime factors. So in this case I had 2 and 3, and in this case I had 2 and 5. So the distinct prime factors between 6 and 20 is 2, 3 and 5. So I'm going to take all the distinct prime factors first, and then I'm going to look the maximum power on those prime factors between these two numbers. Now here between 2, which was common, the maximum power was 2, so I take 2 to the power square 2, and now 3 was only in 6, so I put 3 to the power 1, and 5 was only in 20, so I put 5 to the power 1, which is going to give me 60 as LCM of 6 and 20. Similarly, you need to remember, if you multiply HCF of 6 and 20 and LCM of 6 and 20, what you get is 120. If you multiply first number and second number, which is nothing but 6 and 20, you also get 120. So remember, for any two positive integer, this two positive integer is very important to remember. Okay, for any two positive integers a and b, HCF multiplied to LCM is equal to the multiplication of number itself. Alright, so we can use this result to find LCM of two positive integers if we already found HCF of two positive integers? So now, since we know now this is valid for any two positive integers, and remember this is only valid for two positive integers, and hence if for some reason I know HCF of two positive integer, I can use this formula to find LCM of two positive integers. We'll look into an example. I have to find HCF of 96 and 404 by the prime factorization method, and hence I also have to find their LCM. Now we know we can represent 96 as 2 to the power 5 multiplied by 3, 404 as 2 square multiplied by 101. In this case 101 is also a prime number. Therefore HCF of these two numbers is going to be a common number, which is 2 in this case only, right? And the least power of it, which is 2, between 2 and 5, and hence my HCF is 2 square, which is nothing but 4. Now I'm going to use the formula where I know HCF multiplied to LCM for any two positive integer only. Okay, for any two positive integer only. If you multiply HCF and LCM, what you get is the product of number itself, and hence if I use it and try to simplify it, I'll get 4 multiplied by LCM equal to 96 multiplied by 404, which gives you LCM is equal to 96 multiplied by 404 divided by 4, which gives you 9696. Now let's take another example where I have to find HCF and LCM of 6, 72 and 120 using prime factorization method. I'm going to do the same in this case. I'm going to represent 6 as prime factors, 72 as prime factors, and 120 as prime factors, right? And now I can say HCF between these three numbers are common numbers across, and between all the three numbers the only common number is 2 and 3, and the least power of 2 in all the three numbers is 1, and least power of 3 is also 1, and hence HCF will be 2 multiplied by 3 equal to 6. Next, if I have to find LCM of the three number, I'm going to look distinct prime numbers between all the three numbers. So I have 2, 3 here, I have 2, 3 here common, I have 2, 3 and additional 5. So I'll say 2, 3, 5. Then I'll look the maximum power of 2 between all the three numbers, which is 3 in this case. Even in this case it is 3. So 2 to the power 3. And then I'll look maximum power of 3. It is 1 here, it is 1 here, however it is 2 here. So 3 square, and then 5 to the power 1, because 5 only comes in 120 and it has only 1 as a power. So I'm going to get LCM of 672 120 as 2q multiplied by 3 square multiplied by 5 to the power 1, which gives you 360. Remember, you cannot use 6 multiplied by 72 multiplied by 120 is equal to HCF multiplied by LCM, because this is only valid for 2 positive integers, not for 3 positive integers. However, you should also remember, if HCF of 3 positive integer PQR, you multiplied with LCM of this, and I know this is not equal to product of integers, but then we can use a formula like this where LCM of 3 numbers is equal to product of the 3 number multiplied to HCF of the 3 numbers divided by product of 2 number combinations. So it's product of P and Q, then Q and R, and then P and R. That gives you, so it's P and Q, Q and R, N, R, and P. So it's a cyclic order, right? Similarly, HCF is nothing but same, like it's little different. Like HCF, if you want to calculate, it's the first one is multiplication of all the three number P, Q, R. Now here you are multiplying with LCM as opposed to HCF on the top, because you are trying to find HCF. So LCM of P, Q, R, and the lower side as opposed to HCF is going to be LCM of PQ, QR, and RP. Thanks for watching. You can visit us on www.classisfun.com.